a delight to welcome you to a gathering of Capital City Village, and I'll let you run with it from there.
Okay, thank you, Tom. Rick, we can run the PowerPoint now. And let me add a couple of words to that. Yeah, I actually studied both computer science and astronomy, so I was kind of I specialized in both. And I was not a faculty, I was on the research side of the operation with McDonald Observatory. Okay, so thanks for having me. Good afternoon. So here's the, can we do, there we go. Okay, so now we have it on slideshow. And you've probably seen this, this view perhaps last year sometime. It shows the two main paths of the two eclipses, the one last October, which was called the Ring of Fire, and the one in April this year, which is a total solar eclipse. The one goes, went up to the northwest. This one goes up to the northeast. And the place where they come together was right around Bandera, Texas. Okay, next slide, Rick. Okay, so here's an outline of what I'm going to talk about. I'm going to talk briefly about the sun and what its structure is, and what we can see during observing of the sun in an eclipse. And I do a lot of public outreach. I've done it for national parks for many years, and that includes observing the sun. So I'm going to talk briefly about how I observe it with my own personal solar telescopes. Just because it's interesting and I like the sun a lot, I'm going to summarize some things about the interaction of mankind with the sun over history. A lot of interesting things there. Then we'll get on to the eclipse, talk about the basics, review the previous two eclipses, major eclipses, and then talk about the next one, and then some practical information about observing it safely and tips if you go see it, and so on. Next slide, please. Okay, so I show this to people when I talk about the sun. The sun is a very, of course, it brings us life, and it has a very hot core of tens of millions of degrees. It's doing nuclear reactions which generate the energy that eventually comes to us on Earth. And then it works its way out toward the edge of the sun from the center through both radiation and convective motion, large-scale motions. And then the outer part of the sun that we see, and I know the people online can't see it, but I'll use my pointer. There are various activity things we can see on the outer part of the sun. The part we usually talk about being the edge is the photosphere. There's another layer called the chromosphere. Often there are things called sunspots, we'll see in a minute. Things called prominences, which are eruptions that come off the edge of the sun. And then the thing called the corona, which is that beautiful outer part of the sun you see during an eclipse. Next slide, please. Okay, so one of the main things you see in an eclipse that you don't otherwise see is this beautiful solar corona. It's not very well understood, and it's actually tens of millions of degrees. It's very hot, and it's one of the least understood parts of the sun. So this picture comes from the major eclipse back in 2017 that went coast to coast. So we hope to see that this time in the April eclipse. Okay, one of the things that happens with the sun is there's an 11-year cycle of activity when the sunspots and other activity gets very strong and gets very weak, gets very strong. And this graph shows 400 years of the solar activity, starting in the early 1600s when people started first observing sunspots, and then up to the current time. You can see how the strength of this cycle every 11 years goes up and down. And in the early years in the late 1600s, it was a very weak time of the solar activity. I often make a joke that this thing named after somebody called Maunder was observed this effect. It was almost exactly coincided with the reign of King Louis XIV in France, the so-called Sun King, when the solar activity was at a minimum. Next slide. Okay, so the next question is, where are we in this cycle now? And what will it be like in next month in April when the eclipse occurs? Well, so this shows 2014 was the last major solar maximum. The gray line and the red line were the prediction of solar physicists as to when the next maximum would happen in later this year in 2025. And then the the data shows that we're actually getting more activity and sooner than people were predicting. But the main thing to note is that when this eclipse will be occurring here in April of 2024, we'll be at a maximum in the solar eclipse 11-year cycle. So if you're actually looking through a telescope, odds of getting a lot more sunspots and eruptions off the edge and so on is much greater. Next slide. Okay, one thing when I talk to the public about the sun, I like to talk about is a website called spaceweather.com. And this is updated once a day. And this is a scientific website, and it's all about the relationship between the Earth, the sun, and everything else in our vicinity. So it can include solar activity, auroras, which can come from solar activity, things like meteor showers, comets, all sorts of things nearby in the solar system. And this particular screenshot from a few weeks back shows a large sunspot. Go to the next one. Okay, that same sunspot that was on the left side of the sun has rotated about a week later over to the right side. So the sun rotates about once a month. And so when you see activity on the sun every day, it'll tend to move a little bit around the sun and can have up to a roughly 2-week path around the sun. So that's actually quite fun to watch with small telescopes, because sunspots will come and go. They'll get bigger, they'll get smaller, they'll change their shape. And sometimes they have these dramatic outbursts called flares. Next slide. And this, well, it's about once a month. The sun is 864. That's 109 times the diameter of the Earth. So it's a very large object. I've never actually calculated the speed, but I guess the thing I would point out is in the Earth, and we rotate every 24 hours, right? The Earth is mostly a solid body, so it's rotating, whatever the latitude, the same. The sun is not a solid body, so the rate at which it's rotating varies with north and south because it's not a solar body, but it's rotating very fast. Okay, so this is one more from space weather, and that big sunspot that we saw before is about to disappear off the right side. So it's fun to watch sunspots or other activity on this website. So next slide. And I found another one. I did this talk about a week and a half ago for a UT retiree group. And that morning I logged on and it reminded us that there's actually going to be a comet very close to the sun on April 8th. And because during the totality of an eclipse, the sky gets fairly dark, there's actually a chance we'll actually have or be able to see visually, or at least photographically, a comet very close to the sun, which is unusual. And that would be fantastic. Next. Okay, so there are several very simple ways you can observe the sun. This is the simplest way that's commonly talked about, using basically a pinhole device. You can do it out of a shoebox, for example. So if you make put a piece of aluminum foil with a pinhole and point it right so the sun is coming down through the pinhole, it will project an image onto the back of your shoebox or cereal box or whatever. And so if you put a piece of white paper there, you can get an image of the sun and watch the partial eclipse that way through a little opening you do on the other part of the box. Next one. So here's the common way that the public watches an eclipse. They get eclipse classes, and I'll have something else to say about these a little later. You want to make sure you have safe ones, and there's actually an ISO standard that should be on your sunglasses to be approved, and I'll show you that later. Next one. Okay, then the other way you can look at the sun is with a simple telescope. You can actually project, you can actually project an image back onto a screen or piece of paper, and that has the advantage that it magnifies the sun. So the other simple ones and the glasses will show you a small image, and you can actually see the sun this way. Next. Okay, so I said I've been doing this, observing the sun a lot over a number of years as a volunteer. I've done it for the national parks for 11 years. And back in 2016, which was the 100th anniversary of the national park system, I went out to Big Bend and did several events. And here's an example showing my solar telescopes. I actually use two because they have different filters that show you different things. And there we are. If you've been to Big Bend in the basin, right there by the lodge and the dining room and all that, you'll recognize this spot. So there I am with my national park get up, my hat, my shirt, and my jacket. Next. And so this slide shows you what you can see through the amateur solar telescopes and high quality filters that I use. One of the filters is called a white light filter, and it shows you sunspots and some other activity called faculae. And the other one's called a hydrogen alpha filter, and it can show you these eruptions coming off called prominences. Sometimes these typically around a sunspot, sometimes they'll give off a huge eruption that comes toward Earth of particles and radiation called a flare, and show you a lot of activity that the other one can't. So those two telescopes I have, which I'll have when I go to see the eclipse in April, can show you a lot of activity on the sun in addition to the eclipse. Next. And this is just an example of how big sunspots can get. There have been bigger ones in history, but this is a really big one. So they can be amazing. And then okay, good question. The question is, how far across is the sunspot? The answer is, first of all, the sun is 864,000 miles wide in diameter. Okay, the Earth's about 8,000 miles in diameter. Okay, so the ratio is about 109. So the sun's 109 times wider than the Earth. And then if you take the volume, which is the cube of the diameter or the radius, right, you can actually fit more than 1 million Earths into the sun. That's a fact I often tell people when I'm out with my solar telescopes. So to estimate the size of that sunspot, what I usually do is look at, kind of estimate what percentage of the diameter of the sun that occupies. And this is maybe 10% of that diameter, right? Just as a ballpark. So take 10% of 864,000 miles. That's 75, 85, 90,000 miles in size. And these small cores like this one, the ones on the left, upper left and right, if you're on Zoom and can't see my pointer, those are roughly Earth-sized. So the scale of the sun is amazing. And when you hear about it, then you kind of realize that. But until that's explained, it's not so obvious. Next slide. And then the other kind of filter, that hydrogen alpha, can have amazing views when there's a lot of solar activity, showing these eruptions coming off called prominences, which are basically magnetic storms and flares and all kinds of activity. Yes. We'll talk about that a little bit more. The answer is it can be significant. Yeah. Right. Okay, so the question is, at what point in time are we seeing that? The answer is roughly 8 minutes ago. The sun is 93 million miles away on average. And if you look at the speed of light and do the math, then it's about 8 minutes. Next. And just because I've been a national park volunteer, I put a shameless plug in here that in the last 20 or so years, lots of national parks and also state parks in Texas have started doing really good astronomy programs. And that same year, 2016, I did several at Big Bend. And if you've been to the window viewpoint, yeah, we set up 2 telescopes there. I had the bigger one and Karen had a smaller one. And we had about 75 people in a fantastic telescope viewing star party session in the window view. We're right there, right, there's a little round, there's actually 2 little round areas with the little exhibits and benches and things. We're right there in the, no, it's above it. Right, and then you're looking down directly into the window and the trail that goes down to the window. Yeah, it's great. And then one more, and then we'll move on. We were in one of the cabins up above in the basin, and I just had fun at night with a simple camera taking pictures of the sky. So that's the window at night through at Big Bend. Okay, so let's do a little history and then we'll do the eclipse. So the ancients all around the world were very keen on observing the sky and the seasons and things in the sky, like the wandering movements of the planets and comets when they appeared and eclipses. And just as an example of that, the Babylonians actually observed eclipses and kept a lot of data and logs. It was pretty amazing what the Babylonians did, somewhere around 600 to 700 BC. So they actually recorded whenever they saw an eclipse and kept logs and encoded the information about those eclipses on clay tablets. And some of those still exist. It doesn't say it, but I believe this was in the British Museum. And they started a numbering system called the Saros cycle. So if you're interested in history, you can look that up. But you can still number eclipses, 25 or 600 years later, according to the numbering system where the eclipses repeat, according to the Babylonians. And somebody also pointed out at my last talk that was also an eclipse during the Trojan War. So if you're a glutton for history, you might look that up. Next. Okay, so back in 2019, we took a trip to London just for fun. And it turned out that the London Science Museum, big museum, their special exhibit then was on the sun. So of course we went to it. And it was really good, and they had lots of interesting stuff. So I'm going to talk briefly about some of these things in history about the sun, and then we'll do the eclipse. Let's move on. Okay, the first one has to do with the fact that the ancient people all around the world built all kinds of structures aligned to the sun and where the sun was at the eclipses, and not the eclipses, the equinoxes, sorry, the vernal and autumnal equinox and so on. An example, of course, is, go back. Example, of course, is Stonehenge, but other places like Chaco Canyon is another example. Machu Picchu, if you've been there, has structures that are aligned with the sun. So this happened with all kinds of ancient people over time. Next one. The next thing I really loved about this exhibit is they had one of the most famous books in science and another very famous one. The next one is the heliocentric theory. So up to the time of Copernicus in the 1500s, people thought the sun was the center of the universe. Thought the Earth was the center of the universe, and Copernicus proposed that the sun was the center of the universe, and that set off a debate that lasted a long time before people finally realized the sun was the center. Go to the next one. And so they actually had one of the first edition of Copernicus's book, which is one of the most important books in the history of science, and you can see the proposal of the sun at the center. Go to the next one. Okay, then the next one is about Galileo, who was not just a pioneer using his little telescope to look at the sky, but also to look at the sun. And he wrote a book in which he discussed and showed all his drawings of sunspots. And that also generated a debate about what they were. So are they something between us and the sun? Or are they something actually on the sun? And Galileo argued that they're features on the sun, even though not everybody believed it at the time. And of course, over time, he was proven to be right. And the next one, okay, that's a first edition of Galileo's book showing his sketches of sunspots. Next. And I love this picture, so I show it. Just like I showed that telescope projecting an image of the sun, they did it that way in the old-fashioned days. This is 1630, and you can see how the telescope is projecting an image onto that funny device. Looks unusually complicated for what it is, but it works. Next. Okay, one of the important things that we've seen historically is the fact that these strong solar storms can occur. And that gets back to Rick's questions. If these large flares, as they're called, usually called X flares when they're really strong, occur, they can shut down power grids, interfere with radio communications, interfere now with GPS and all this technology we have. So the most famous one that happened was in 1859. A British astronomer named Carrington, and you can go to the next slide. Carrington was looking through his telescope and making drawings of the sunspots, and he saw this huge flash, basically, when the sun got incredibly bright. And so it's generally believed out of the last 400 years, he he observed personally the largest solar storm we've seen in the last 400 years. This is just, they actually had his logbook of all kinds of data. Go next. And so this exhibit had some really nice animations of what happened during this solar storm. So I'll show that. Of course, this is not the scale, but when these flares happen, they're emitting this huge cloud of radiation and particles and out into space. And if the sun's rotation is such that it's pointed fairly directly at us, we can then have that huge consequence from it. Go to the next one. So some of the things that happened or were observed from that 1859 event were, by then they had telegraphs, and people noticed arcing on telegraph wires, and somebody even reported this telegraph wire catching fire because of the electrical disturbance that the event caused. Go to the next one. This illustrates how strong aurora can result. We get aurora anyway from natural phenomena. But when the solar activity is the strongest, we get the very strongest aurora. So people observed incredibly strong auroras. Next. I like this one a lot. People out on ships noticed that the sea was almost turned red from the reflection of the reddish colors onto the sea. And one ship even, before they looked up and saw the auroras, thought there was blood in the ocean. Strange times, eh? Next. And so to conclude that, sooner or later, we'll have another huge storm. We just don't know when, and it'll be interesting to see what it does to all our modern technology. Next. Okay, a couple more, and then we'll be on to eclipses. At all the major eclipses, scientific societies and institutions have sent expeditions out to observe things and learn what they can. So this is one from 1860 as an example of the old-fashioned way of doing that. Next. So one of the interesting things that happened was that in 1868 in an eclipse, they were using a spectrograph which broke the sunlight into the rainbow of colors, and they observed features in that spectrum that they had never seen before. And so they theorized that it was another element they had never discovered here on Earth. And of course, what did they call it? Helium, after the sun. So helium was discovered as a result of a solar eclipse. And this is an astronomer, Norman Lockyer, who was a Brit. You'll notice on the bottom, another astronomer in France saw the same thing in the same eclipse. And we go to France a lot. And I've seen references to Janssen in France. And if you're in England, it was Lockyer that discovered it. If you're in France, they only talk about Janssen, not Lockyer. Question? It's primarily hydrogen and helium because the nuclear reactions begin with hydrogen, form helium, and eventually they work their way up the periodic table, carbon, nitrogen, oxygen, and then eventually they go up to the higher elements like iron and manganese, and eventually the process stops generating energy and it can start consuming energy, and then catastrophic things can happen. Like if the star is supermassive, it can explode as a supernova. We won't get into that. So the answer is primarily hydrogen and helium, and then a lot of very smaller trace quantities of higher elements. Yeah, the sun is very hot. Yeah, it's what we call a plasma on the surface. Okay, two more to go on this, and then we'll be on to the eclipse. One of the most important things that happened with eclipses was there was a big eclipse in 1919, and Albert Einstein had proposed his theory of relativity a few years before, and he had actually proposed that strong masses could bend starlight. And before this time, it had been theorized that there might be another planet in the inner solar system. We know about Mercury, right, the closest to the solar system. But in the 1800s, astronomers had noticed anomalous motions of Mercury, and because of that, they proposed that maybe there was another planet that we hadn't discovered yet. They called it Vulcan, and they could never find it. If you know anything about solar system, you'll know that Neptune was discovered because an astronomer also discovered irregularities in the motion of like Uranus further out. He predicted where that Neptune should exist, said right where it was, and an astronomer with a telescope discovered it. Well, Einstein predicted that we would actually see Mercury at a different place during an eclipse. And this diagram summarizes that. So from our vantage point on the Earth, looking close to the sun, the star appears to be in one place, and its actual location is a little bit off. This is greatly exaggerated, so the effect is really quite small, not as huge as that shows. And so the result of this was Einstein's theory was confirmed, and it was understood why Mercury's orbit was a little bit off. Okay, one more here. One other thing they had that I liked a lot at this exhibit was a lot of information about spacecraft that NASA or other Europeans or whatever had put up. And they had this beautiful exhibit of all these different spacecraft, and that's just a list of them. And they've revolutionized our understanding of the sun. All right, so let's move on. One more slide. Probably the strongest solar flare that's been seen in recent times that could have caused a major impact on Earth was one that happened in November 2003. And one of those spacecraft called SOHO actually recorded this massive outburst. That little white circle in the middle it's an occulting disk, so the main light of the sun's blocked out in this spacecraft, so you can see the outer part of the sun around it. And so the white circle shows you the size of the sun as we see it. You can see that this huge solar flare was several times the size of the Earth. The bad news was it was really strong. The good news was the sun had rotated, so that was almost pointing off to the side. So if that had occurred about a week earlier and been pointed at us, 21 years ago, it may have been, quote, the big one. So let's move on. Well, one thing space weather does is they predict. They tell you which sunspots have the really strong, complex magnetic fields and potential to produce this kind of thing. And so people can give you probabilities of risk, and those things exist, but you never know when it's going to go off. Okay, so let's continue with eclipses. All right, so here's the basic geometry of a solar eclipse. Of course, the eclipses occur around new moon, at new moon, when the moon is between the Earth and the sun. And because of that, the moon casts a shadow on the Earth, and that shadow is moving across the Earth as the moon slowly moves through the sky. And when you're within that shadow, then you're experiencing the eclipse. Pretty straightforward. There are some complications because the orbits aren't exactly circular, and they're not, the planes of the orbits aren't perfectly aligned. So there are variations from eclipse to eclipse, but that's the basic phenomenon. Next. Just for completeness, here's a NASA slide that shows you what happens when a lunar eclipse occurs, and that's just the opposite. So that occurs when the Earth is between the moon and the sun, and in that case, the Earth is causing a shadow from the light from the sun, and as the moon travels through it, we see the moon getting darker and being eclipsed. Next. Okay, so I like to explain this when we talk about eclipses, just, well, why do they happen? And it turns out there's a thing called the, quote, 400 coincidence. Has anybody heard of that or seen that on TV yet? Okay. All right, so this slide kind of explains that, okay. Okay, the first thing is, remember I said the sun is 864,000 miles in diameter. The moon is about 2,150 miles in diameter. You take that 800 and something thousand divided by the 200,000, that's about a factor of 400, right? Well, it turns out that the sun on average is about 400 times further away than the moon. So what does that mean? That means when you see the sun through a telescope on the sky or a filter like an eclipse glass, or the full moon at night, they're almost exactly the same size on the sky, right? So whenever the motions are such that they line up, we can actually get that eclipse. So if it weren't for this factor of 400, we wouldn't get eclipses. That's just kind of a quirk of nature. And as I said, the planes of these two orbits are not quite the same. The moon's distance varies a little bit. The sun's distance a little bit because their orbits are not quite circular. And so every time there's an eclipse, the geometry is a little bit different. So you'll get a partial eclipse, a total eclipse, a ring of fire. They'll have different lengths of totality and different details, varying for each eclipse. And just turns out the one in April, it's almost the best geometry we can have, so it's a really good one. Next. Okay, so if you have your eclipse classes, this is kind of what the full duration of a solar eclipse would look like. They typically take around 3 hours. And if you experience the one in October, the Ring of Fire, it started about an hour and a half before that maximum ring occurred and continued afterward for another roughly hour and a half. And if you have eclipse glasses, you'll see a nice image of the sun that's fairly small. It's big enough that you'll see the sun going from a full disk to gradually to that little crescent. And then during totality, that's the only time you can safely look without the glasses. And then the reverse happens. So that was from the 2017 eclipse. Next. Just a little terminology for the record. As the sun moves across, as the moon moves across the sun gradually during those 3 hours or so, when they first come into contact, that's called first contact. And then you have this partial phase. And then once the total eclipse starts, you have a third contact when it starts totality, and then the fourth contact when totality ends, and second and third contact, and finally fourth contact when the eclipse is completely over. So you might see those terminology. Next. Okay, here in the 2017 eclipse, these are two really good photographers, one from NASA and another person who got it from Kentucky. And it shows you how the progression and the totality occurs and how that solar corona comes out during the eclipse. Notice in this bottom one, and that the corona showed these three parts, kind of like two ears and a goatee, two to the upper right, one to the lower left. So go to the next one. That's just the angle, and I think it's the processing they did. I think that's just an artifact of the photographers and maybe the telescopes and how their cameras were aligned. Okay, so a few statistics. Each century, there are a couple of hundreds of eclipses, so they're actually fairly common. But the place you can see them best on Earth changes all the time. So at any given location, you only get one every so often. So roughly similar numbers last century and this century. Next. That's coming. That'll be in a future slide. Team, yeah. I have that. So I've got a few slides from the last two, and then we'll talk about this one. Okay, so the last one, the Ring of Fire. This was the best image I could find of a photographer who caught the perfect alignment when the sun was eclipsed, but not totally, because that outer bright ring was still dangerous. So this is an example of the distances being such that the solar image is a little bit bigger than the lunar image, right? So it was not a total eclipse, but it was an annular eclipse, we call it. Annular meaning, like a donut. And so that's a really good example of the Ring of Fire eclipse. Next one. Okay, we went out to Fredericksburg for that one. There I am with my bright colored shirt and UT hat on with my telescope with two small telescopes. People often see these and they're expecting a big telescope, right? At night, you'd want to see a big telescope, wouldn't you? Well, with the sun, you don't need a big telescope. You don't want a big telescope. You want one with a really good filter that gets rid of light, right? So they're not that big, but they're really good. Okay, so I had my two telescopes. That's what you usually see is everybody looking up at the sun. That's Karen with her eclipse shirt and a friend of ours looking through his binoculars with binocular filters on it up at the eclipse. One more. And one of the cool things about this when we went to Fredericksburg and set up on that marketplace in Fredericksburg was right when I was setting up, a group of about 10 students and a professor came by turned out there was a UT geology professor, and she had this program for high school students. They'd come every weekend, and they'd do some science topic. And for the eclipse, she took them to Fredericksburg, and they saw my UT hat, and they realized that I was an astronomer. And so they hung around for pretty much the whole eclipse, and there's one of them looking through the telescope. So yeah, often when you're doing public outreach, interesting things happen. Okay, next. Okay, so now we're on to the 2017 eclipse, briefly. Okay, so here are two pictures from that. The one on the right shows the path of the 2017 eclipse, and it went all the way from Oregon in the northwest down to South Carolina in the southeast. You know, and tens of millions of people went to all kinds of places along the path of the 2017 eclipse. As it says in the lower right, in August of 2017, I was doing a national park astronomy volunteering at Black Canyon of the Gunnison National Park in western Colorado. And this happened on a Monday, and it turns out that one of Karen's brothers lives in Nebraska, central Nebraska. It's about 600 miles away to get to the center line. So we drove to her brother's house and observed the eclipse from there. And we didn't have to fight the traffic or anything. And I put the left image on just because I like this image so much. This photographer's obviously fantastic technique, and this is obviously multiple exposures. It not only shows the corona in wonderful detail, but he actually captured the full moon. You can actually see the bright and darker regions on the full moon in his eclipse photo. Okay, next slide. So here we are in Kearney, Nebraska, in the backyard with my telescope. Hera and her brother, one of her sisters, and a husband. And next slide. Okay, so I didn't go out of my way to do any fancy photography. I just wanted to experience it and see it. So there I am with my telescope. I actually just took a few pictures with a good camera, not a phone, but a better camera than a phone, through the eyepiece. And I actually caught the eclipse when it was just before totality, showing a crescent, and just after totality when it was the opposite crescent. And then during totality, I actually put my camera on telephoto and took a picture of it. And I actually got a respectable photo just with an ordinary camera. Wow. During totality, the eclipse and the sun is roughly the same brightness as a full moon. So it's safe to do that. You just have to be careful, the beginning and the end, that you don't catch the bright sun. And even in my little picture on the lower left, you can see that little appendage coming out in the two in the upper right. And if you looked at this photo in closer detail, there's actually a bright star close to the sun. So the sky gets dark enough and there's bright stars nearby, you can actually see bright stars during the totality of an eclipse. It's not full darkness, but it can be reasonably dark. And I think that depends on the length of totality that you have. If you're in a place where the totality is short, it's not going to get quite as dark. If you're in a maximum totality in the middle, it's going to be a little darker. Next slide. Okay, I did have some fun, and you can have fun too. Start with the right. Common thing is people use a pinhole or something, but colanders work really well because they have all these little apertures on them. So there, upper right, there's me projecting the image of the image of the sun onto the concrete patio. There's my image of the solar eclipse on the concrete patio. On the left, this is one of my favorite photos ever. Before the eclipse started, when the sun was still a full disk, did that again. Okay, I got a picture of the full disk of the sun, and you can see my left hand there, my right hand here, and you can see that bright colored shirt. And you can actually see the camera and my finger on there getting ready to take the picture. And that was just kind of an accident with reflections coming off the glass and the eyepiece. And I wasn't really expecting that, but I really like that picture. Okay, the other thing we did when we were in Kearney, since we were in a house, we didn't have to go out and fight the crowds to get to the very best spot. It was close to the University of Nebraska at Kearney. They had an event going on. So we had the TV inside on NASA TV, and they were going around the country giving a blow-by-blow account the eclipse in different places. That was kind of fun to go in and out and watch. And so if you stay at home and do it, you have NASA TV. Well, of course, now you could probably get some online feed or YouTube or things other than NASA, but NASA's an obvious one. So that's another way to observe the eclipse. And one of my favorite stories about this one was the eclipse was in the middle of the day. And that evening on the local news, they interviewed a student. And the eclipse happened on August 21st, 2017. It was a Monday. Now, it just happened, this was the first day of class at the University of Nebraska at Kearney. So they asked this guy, what he thought of his first day, and he said, it was fantastic. They let school out for 3 hours. We had a big event in the football stadium, and I love school. School's great. College is great. I think the next day was a little harder. Next one. Oh, the end of the eclipse, we had good weather and it was great. Next one. Okay, so this one coming up. Okay, so here's another picture from NASA showing the path of the eclipse in April. And the shadow will start out in the Pacific Ocean, work its way up through Mexico, through Texas, and go all the way to the northeast through the upper part of Vermont, I think, and Maine and into Nova Scotia over an extended period of time. You'll notice the two marks in Mexico. I think you'll understand why that's probably there shortly. Let's do the next slide. Okay, there are people who keep track of cloud statistics and things like that. And at this website, eclipsophile.com, they produced a long-term record of cloud cover for this day over history for various locations. On the left is the Pacific Ocean. This is in central Mexico. Texas is here on the left side, Texas, Arkansas. And basically, as you go along that line from Texas to Maine, the probability of clouds gets higher and higher. Okay, the probability for at least clouds part of the time is kind of 50% in Texas. And it's not that different from Uvalde to northeast Texas. But that explains partially why so many people want to come to Texas, because the probability of good weather is highest. It also explains why some of the professional astronomers and truly serious eclipse watchers go to Mexico, because their chances are even better. Yeah. Well, we haven't decided for sure. We'll probably head toward Cedar Park, maybe toward Burnett, out in that direction. And you'll understand why in a minute. The other reason is Karen's sister her husband has relatives there. And if they want us to go there, we'll go there. Cedar Park will have over 3 minutes of totality. So it's noted for only, 20 miles or so. It's noticeably better than downtown Austin. Mm-hmm. Well, not as good as we do. And I'd point out another thing too. And it could be totally cloudy or raining, and you could have no chance. It could also be partly cloudy, and the clouds could come and go. And if the clouds are light, you could probably still see some of the eclipse. And not only that, but you would still feel the effects of the sky getting darker and some other things that we'll see shortly. Okay, next. All right, so I made a chart showing the length of totality and when it starts for various places in Texas. So Concan and Kerrville are right on the central line. Concan is down by Garner State Park. So that's about 175 miles from Austin. Kerrville's about 100 miles. San Antonio gets 2 minutes roughly. Stonewall, before you get to Fredericksburg, is really good. It's over 4 minutes. Dripping Springs, pretty good, 3. Cedar Park, I just mentioned, is over 3, so that's pretty good. If you're in downtown Austin, it's less than 2, but still, not bad. And then it goes very close to Waco, so, Waco is a pretty prime spot too. And you can see when totality is around 1:30 Central Daylight Time. Next. Okay, so it's kind of hard to see, but this is just some detail that it shows you. There's San Antonio in the bottom, Austin on the right, Kerrville and Fredericksburg in the middle. And it's just showing you how long totality is as you go toward the central line up around Kerrville and Fredericksburg. And and Burnett, and Lampasas too. And then as you go further north and west, your totality time goes down. Next. And this one's kind of scary. This is another one from another website where they've attempted to predict the total number of people that'll go to these places. Okay, so I don't know if you can read those numbers, and they're not very good about identifying the towns, but this is Kerrville right here. Their prediction is anywhere from 122,000 to 488,000 people. Well, I mean, a lot of them have reserved places in advance. They're probably paying a lot. A lot of them are probably coming up from San Antonio because the interstate goes directly from San Antonio to Kerrville. Yeah, we'll see what happens. Yeah, and that's a no-no, but they could do that. And you can't read all these very well, but here's, oh, that's Eagle Pass, Uvalde. Actually, go back to the previous slide, Rick, please. Yeah, you can see here, San Antonio at the bottom, here's Interstate 10. It goes straight to Kerrville. If you're in San Antonio, why would you want to go up to Austin or Cedar Park? The only reason you might want to is if weather forecast the day before said it's good chance for clouds or rain in the southwest part of Texas. It's going to be a lot better near Austin or Waco or Dallas. But anyway, that last one shows you how easy it is to get from San Antonio to Kerrville. And by the same token, how going from Austin out toward the northwest is much closer. Question?
Okay, we are leaving on an airplane at 1:05 that day and flying to Philadelphia. What can we see?
I guess it depends on the path of the plane. There is a Delta. Maybe some of you saw on the news. Is it the Delta flight? Not the Delta flight. Delta's doing a special flight. I think it's because they just happened to be going toward Detroit, was it? Someplace kind of along the Eclipse line. So they increased the price and said they're going to follow the Eclipse line. And I think that sold out really fast. Now, as far as yours goes, I would hope that they would say, well, let's try to see the eclipse if the conditions permit. So I think the answer is I don't know, but good luck. That would be fun. Pardon? That's true. Yeah, I mean they could do it if they tried. Yeah. In the plane or on the ground? It'll be fairly dark. Yeah, Tom has a question.
Beginning of your lecture on the cycles of the sun,
Uh-huh.
those 11
11-year cycle.
Exactly. Is there a discernible effect on U.S. temperatures on the Earth during those cycles? Any changes that happens?
There's anecdotal estimates from the past that Maunder minimum in the second half of the 1600s was a very cold period on Earth.
Right.
But that doesn't necessarily say anything about the rest of the Earth or whether the average temperature was lower. So there have been studies that say there is a small effect, but I'm not an expert on that, so I wouldn't really want to comment on that.
Well, and it's probably fairly transient too.
It could be. Mm-hmm.
Yeah, thank you.
Okay, so
Another
let's
question?
anyway. So to finish this slide, the predictions for Uvalde and Eagle Pass are just thousands of people. That's not very high. The predictions up in which one is that? Well, to the northwest, are anywhere from 2,000 to 16,000 out toward Cedar Park, Burnett, Lampasas, that area, and that's Dallas. And Waco, north of Waco, maybe 15 to 60. So we're going to the northwest is pretty good. Let's go to the next one. A couple of things that happened. There's something called Bailey's beads, and you're unlikely to see this visually, but photographically you could, because the moon actually has mountains and topography on it. So when the moon is just about to totally eclipse the sun, either the beginning of the totality or the end, you can actually get that last remaining light of the sun break into little individual beads. So if the mountain's blocking the sun, you don't get the light. it's between a valley between the mountains, you could see a little bead of light. So Bailey's beads is one thing. Next one, then the diamond ring effect. And so again, right before or after eclipse, you can actually see something that looks like a diamond ring. Next. Okay, so I mentioned that because the moon is moving and throwing that shadow onto the Earth, and that shadow is slowly moving across the Earth. This picture on the left shows you what that shadow can look like moving across the Earth. And so when you're actually getting ready, we're actually watching the eclipse and getting fairly close to totality, you can actually see that darker region coming, and that people say, I don't remember it from 2017, but see that shadow coming across the ground towards you. They also say because of the things called shadow bands, and that's because the atmosphere can create little effects where you have darker shadows and lighter shadows and so on from atmospheric effects. Say that again. I would think so. Yeah, I don't know. That's a good question. I haven't thought about that. Next slide. Okay, one of the things that happens is you get strange behavior, not strange, but unusual behavior from animals. And this is pretty much reported at every eclipse. And that's because, skies get darker. So when you get closer, at the beginning, not much of the sun is eclipsed. So you won't feel too much of a change in temperature. But as the sun is, down to maybe 25% or 10% of its usual brightness, not only do you start to see it getting darker, but the temperature will start going down. And so these darker skies and cooling temperatures signal nighttime to some animals. Some people call that the twilight zone, but things change atmospherically, the temperatures and lighting and so on, wind potentially. And so animals react to that. So some animals think it's evening coming, even though it's not evening. Animals start making sounds, chirping, for example. If they're resting during the daytime and they're nocturnal, they might want to come out, right? That's kind of the opposite effect. So I love this last one. This is from a paper by somebody, a biologist at Indiana University. I liked her list. It says that vigilant baboons huddle together. I would like to see a picture of that. I don't think vigilant humans would do that, but you never know. Okay, so there are lots of ways to view the sun safely while it's not in totality. This is just some examples from a friend of mine in Colorado. First of all, just because of the fact that the sun has a lot of light and it can be dangerous to look at, if you actually put crosshairs in a telescope at the focus of the telescope, it will melt the crosshairs. That's an example of that. If you put a solar filter like let's say a neutral density 5 or a welder's glass in a telescope, and without realizing that it's dangerous, that concentrated light can hit it and crack the filter, crack the glass, because it's concentrating heat in the telescope as well as light. Okay, so that's that one. The next one, top center, the pinhole, we saw that before. The one below that, the projection, we saw an example of that. Upper right, the colander, we saw that. In the lower left, there's a thing called a sun spotter. Some people make it and sell it, but it's kind of expensive. So you can actually make little gizmos with the pinhole that have a nice screen and a nice projection. And if you look at the sun a lot as an amateur in public outreach, that might be an interesting thing to have. Then, of course, the eclipse glasses. Number 14, welder's glass, has the right properties to be a good filter. Telescopes also have either glass or mylar filters that you can put on your front of your telescope and get a good image of the sun. The basic spec that they need to do is let through about 1 part in 100,000 of the light. Okay, that's the strength of the filter that makes it safe. The next one shows an example of a filter like that on the telescope, and then the last one on the lower right. A lot of amateur astronomers now hook up high-powered, sophisticated cameras and into their computer, and then collect images into their computer and display the image on their laptop computer, for example. So that's a common way to do it. Yes. Uh-huh. I hope so. Yeah. Any reputable company would do that. And that leads us to the next slide. Okay. Important. Okay. Okay. This, I mentioned earlier this ISO spec. And let me get this. Oops. Okay. This is an example of the ones McDonald Observatory made. And these are not glasses per se, but they're wide and you can hold them up in front of your eyes. And if you look on the back, you'll see this ISO number. So maybe you should just pass that around. So that's the magic number, ISO 12312-2 from 2015. So anything you buy should have that ISO on it, and you should see that number before you buy it. Well, these McDonald's giving these out, but you can buy these on Amazon, or if you Google it, you'll find
REI,
lots
you
of
said
places.
have it.
And if you have one, look at it carefully. Make sure it's not scratched or didn't get a little hole in it or something. So, you know, if it's damaged, don't use it, of course. Next. Okay, a few more slides and we're done. Some details. If you go out and viewing the eclipse, make sure you can do it safely. And never look at the sun directly except during that short period of totality when it's safe. Public events are great if you can go to one. There'll be a lot of people at UT. I've heard they're canceling class. So there'll probably be lots of people around UT and bound to be some telescopes set up and whatever. So public events are great if you have one. The Austin Astronomical Society is supposed to be doing one at Pedernales Falls. And I think on Friday, I think this Friday, the state parks are opening up reservations for people that want to go to state parks and view the eclipse, whether there's an event or not. And I'm guessing there'll be a massive demand for that. And the one at Pedernales Falls, I'm not sure about, but how many people. But anyway, public events by reputable organizations are good. If you head out for a while, you know, take water, food, etc., sunscreen, hat, chairs. You want to enjoy it. Watch the weather. There are people who will chase the eclipse. Okay, so they'll be watching, and if they think they need to go an hour this way, hour that way to get clear weather, you know, they'll be doing it. Beware of traffic. You know, those things about 500,000 people in Kerrville. I can't imagine that, but they could try. Allow plenty of time. Okay, as I said, as you're getting closer within, you know, 10 or minutes or whatever toward totality, at some point the shadow will be approaching. Temperatures changes will be apparent. Listen for things, animals changing their behavior. As I said before, there may be bright stars visible if it gets dark enough, and enjoy it. Next. Okay, one of the best examples, and I'll show this at the end, website if you want to learn more about eclipses, a magazine called Sky and Telescope. It's now owned by the American Astronomical Society, so it's a very high quality content source. And they have a list of lots of events, so I just put them in here for the record. You know. And the first four are, there's one in Rodeo Arena in Bandera. There's one at a vineyard in Fredericksburg. There's one in Lampasas, another one in Lampasas. Probably lots of wineries out by Fredericksburg will be having them. Next. The next one's Gatesville. That's up near Fort Hood. The next one is in Burnett County. The third one is in Burnett. The fourth one's in Ingram. That's west of Kerrville, so that's probably hopeless to get there unless you go the day before, but they're having an event. There's one more of these. Quiet Valley Ranch in Kerrville. That's where they have the Kerrville Folk Festival, and that's a pretty big area, so that's probably really good. Then there's a big public park in Kerrville, and the last one's the football stadium at Baylor in Waco. So that'd probably be pretty good, right? Okay, just a couple more slides. Okay, people often ask, when's the next good eclipse? Well, there's two pictures on here. The one on the left, there's one this October, and you can see its path. It's only annular, like the Ring of Fire, so it's not total, but it's going through the Pacific Ocean and far South America. And this just brings up the fact that there are actually cruise ships that go out and do eclipses. So if you like cruises and you're interested in eclipses, you can search around for those. And the one on the right, in 21 years, the next total eclipse of the sun that goes coast to coast will occur in August of 2045, and it'll come in Northern California. It go all the way toward Florida. It'll go through Kansas and Oklahoma, but not Texas. Probably not.
I've got a reservation to sell you.
And if you really love Oklahoma, like a lot of people in Austin do, here's your chance to go to Oklahoma. Next. Okay, as a summary, I like this. UT McDonald Observatory has a magazine and a website and a radio program called Stardate. They had a nice little article. Do's and don'ts of eclipse watching. This was their summary. Look at it. During totality, it's safe, so you can look at it then, but it's not safe otherwise without the proper filter or telescope. Plan ahead. There may be large crowds and so on. Check the weather, because you may want to have an alternate plan. Things you don't do is look at it directly when it's not fully eclipsed. Don't park on the highway shoulder. I've already heard at least one TxDOT person warning about that. I'm sure when it gets closer, the news stations will have all sorts of things about that. And photography is fun and cameras are fun, but don't waste your totality by messing around with your camera. Just enjoy it and watch it, unless you've seen lots of these and you're ready to do some serious photography. I mentioned Sky and Telescope before. If you find Sky and Telescope's website and look for the Eclipse Guide, it's a fabulous source. It has all kinds of links to specifics about the eclipse. And as I said, it's a part of the American Astronomical Society now, which is obviously a top organization. Next slide, the last slide. So enjoy it. Thanks for listening. And any more questions? Okay.
With a small telescope and no filter on it, can you wear the glasses and look through the telescope? And
I wouldn't do that. No. I would, if it lends itself to projection, is it like the refractor that has the image at the bottom? Yeah, you could take a nice white, bright, piece of photo paper or whatever and project the image onto it, but you'd have to be very careful. I would use the glasses. I would use look at NASA TV or whatever. Make sure you know what you're doing. If you have friends and they know what they're doing like I do, then it's perfectly all right. But you have to be careful.
Other observations other than, may I tell you what a wonderfully exciting hour you have given us.
Ooh, other observations. Just enjoy it. We hope for good weather and plan ahead. And if you can find an event or somebody like me where you have telescopes, that's great. Even if you don't go somewhere where they have good solar telescopes, you go to state parks or national parks, look for public programs, and you can see solar activity and really good nighttime viewing in parks. So I'd recommend that also for the future. Thank you.